Assalamu alaikum. In this video, we discuss the last part of the chapter Work and Energy. I recall the objectives that have been studied. The work done by a constant force, the work done by the weight, the kinetic energy, the gravitational potential energy, and the mechanical energy. In this video, we discuss the last objective, which is the principle of conservation of mechanical energy. To understand this principle, let's discuss the following animation. This animation consists of two passes, inclined pass and horizontal straight pass. And we have four indicators. The first one for the kinetic energy, the second one is for the gravitational potential energy, the third one represents the work done by the resistive forces, and the last indicator represents the total mechanical energy. Along the inclined plane, we can see that the total mechanical energy is constant and the work done by the resistive forces is equal to zero. So, if the work done by the resistive forces is equal to zero, then the mechanical energy is conserved. That means it remains constant at any instant t, which indicates that the variation in the mechanical energy is equal to zero. So, the initial mechanical energy is equal to the final mechanical energy. An example about conservation of mechanical energy is shown here. The person releases down an object and we assume that the air resistance is neglected. The gravitational potential energy is converted into kinetic energy. However, their sum is always constant. So, in case the mechanical energy is conserved, we obtain a horizontal straight line as shown here in the yellow line. To understand the cases where the mechanical energy is not conserved, let's discuss the second part of the animation along the straight path. The kinetic energy decreases and the mechanical energy also decreases. However, the work done by the resistive forces is less than zero, as shown here. So, if the work done by the resistive forces is less than zero, then the mechanical energy is not conserved due to the presence of resistive forces, which indicates that the variation in the mechanical energy is less than zero, and this variation is equal to the work done by the resistive forces. Also, the mechanical energy may be not conserved due to motive force. To practice on this principle, let's solve application 5. We have a ball that releases from point A toward point B, then it rebounces back from B toward point C. In this problem, we have to analyze the energy conversion that takes place during falling down and during the rebouncing back. In this problem, we have the mass of the ball is 400 grams and the speed of the ball at point B is 5 meters per second, and the reference plane for the gravitational potential energy is passing through the point B, and we neglect all the resistive forces. In first part and during falling down, the first question is specify whether the ball gains or loses gravitational potential energy. The answer is easy. Since the gravitational potential energy is proportional to height, and as height decreases, so the gravitational potential energy decreases. So the ball loses gravitational potential energy. The second question is to determine the kinetic energy of the ball at point B, and we have to deduce the mechanical energy of the system at point B. The expression of the kinetic energy at point B is equal to half mvb squared. So we substitute all the values and we get 5 joule. The mechanical energy at point B is equal to the sum of the kinetic energy at B and the gravitational potential energy at B. But the gravitational potential energy at B is equal to 0 since point B is at the reference level. So the mechanical energy at B is equal to the kinetic energy at B is equal to 5 joule. The third question is to determine the mechanical energy of the system at point A. In the given of this exercise, the resistive forces are neglected. So the mechanical energy at point A is equal to the mechanical energy at point B due to the conservation of mechanical energy. So the value of the mechanical energy at A is equal to 5 joule. The next question is to calculate the altitude HA of the ball at point A. In order to find HA, we have to calculate the gravitational potential energy at point A. We know that the mechanical energy at point A is equal to the kinetic energy at point A plus the gravitational potential energy at point A. But the kinetic energy of the ball at point A is equal to 0 because the ball falls from rest. So the gravitational potential energy at A is equal to the mechanical energy at A is equal to 5 joule. The expression of the gravitational potential energy at A is equal to mgHA is equal to 5 joule. So we make a simple calculation and we get H equal 1.25 meter. The question 5 is to calculate the sum of the work done by external forces. In this problem, we neglect all the resistive forces. So the only force acting on the body is its weight. The work done by the weight is equal to mgHA minus hb. We make the substitution of all number and we get 5 joule. In the question number 6, we have to verify that the variation in the kinetic energy is equal to the net of the work done by all external forces. The variation in the kinetic energy is equal to kinetic energy B minus kinetic energy A. We know that kinetic energy B is equal to 5 joule and kinetic energy A is equal to 0. So the variation in the kinetic energy is equal to 5 joule. 5 joule is equal to the work done by the weight is equal to the net work done by all external forces. So this relation is verified. Now we discuss the bouncing back of the ball from B to C. After it hits the ground, the ball loses 10% of its kinetic energy and it reaches to maximum point at point C. The first question is to calculate the new kinetic energy of the ball at point B. The kinetic energy at point B is equal to 90% of the initial kinetic at B. 90% correspond to 0.9 times kinetic energy at point B. We substitute and we get 4.5 joule. Then we have to deduce the mechanical energy at point B. The new mechanical energy at point B is equal to the new kinetic energy plus the gravitational potential energy at point B. But the gravitational potential energy at point B is equal to 0. So the new mechanical energy at point B is equal to 4.5 joule. The next question is to determine the height of C using conservation of mechanical energy. The mechanical energy at point C is equal to the mechanical energy at point B. So it is equal to 4.5 joule. But the mechanical energy at point C is equal to the kinetic energy at point C plus the gravitational potential at point C. But the kinetic energy at point C is equal to 0 since C is the maximum height. Then the mechanical energy at point C is equal to the gravitational potential energy at point C is equal to mgHc. So mgHc is equal to 4.5. Then we make a simple calculation and hc is equal to 1.125 meter. To more practice, let's solve application 6. We have a solid of mass m equals 0.1 kilogram is launched with 10 meter per second toward point B. Then the solid is returned back. The plane passing through the point A is taken as the reference for the gravitational potential energy, and we have G equal 10 meter per second square. We have to study the energy conversion of the solid during moving up and moving down. In the first part, the solid S rises from A to B. We have to calculate the mechanical energy at point A and the mechanical energy at point B. The mechanical energy at point A is equal to the kinetic energy at point A and the gravitational potential energy at point A. But the gravitational potential energy at point A is equal to 0 since the height is equal to 0. So we have the kinetic energy is equal to 0.5 mv square. We substitute and we get 5 joule. The mechanical energy at point B is equal to the kinetic energy at point B and the gravitational potential energy at point B. But the kinetic energy at point B is equal to 0 because the ball stops at point B, then moves back. So the speed at point B is equal to 0, so the kinetic energy becomes 0. So the mechanical energy at point B is equal to the gravitational potential at point B is equal to mgHp. We make a simple calculation and we get 4 joule. The next question is to determine the variation in the mechanical energy. Then we have to deduce the presence of the resistive force. The variation in the mechanical energy is equal to the mechanical energy at point B minus the mechanical energy at point A. So 4 minus 5 is equal to minus 1 joule. It is less than 0, so the resistive force exists. In the third question, we have to calculate the magnitude of the friction force along the track AB, knowing that AB is equal to 2 meters. It's given that the variation in the mechanical energy is equal to the work done by the resistive force. So delta mechanical energy is equal to WF. Delta mechanical energy is equal to minus 1. It's equal to minus F times AB. Then F is equal to 1 over B is equal to 0.5 Newton. Now we discuss the second part of the application. The solid S is moving down from point B toward point C. It reached point C with a speed equal radical 80 meters per second. It's given that the variation in the mechanical energy is the same during upward and downward motion. The first question is to calculate the mechanical energy of the system at point C. We can use this given. The variation in the mechanical energy is the same during upward and downward motion. So the variation in the mechanical energy between B and C is equal to mechanical energy at C minus mechanical energy at B. Then mechanical energy at C is equal to delta mechanical energy plus mechanical energy at B. So minus 1 plus 4 is equal to 3 joule. Now we have to calculate the altitude of S at point C. The mechanical energy at point C is equal to the kinetic energy at point C plus the gravitational potential energy at point C. But the gravitational potential energy at point C is equal to minus mgHc because C is below the reference, passes through A. Then the gravitational potential energy at point C is equal to the mechanical energy at point C minus the kinetic energy at point C. So we substitute and we get minus 1 joule. Then minus mgHc is equal to minus 1. Then we perform a simple calculation and we get Hc equal to 1 meter. At the end of this video, let's summarize the main point. The principle of conservation of mechanical energy indicates that the initial mechanical energy is equal to the final mechanical energy. The non-conservation of mechanical energy due to resistive forces indicates that the system loses energy and the initial mechanical energy is greater than the final energy. The loss or the decrease in the mechanical energy will appear in the form of heat. If mechanical energy is conserved, then the variation in the mechanical energy is equal to 0. And if the mechanical energy is not conserved, then delta mechanical energy is different from 0, and in case of resistive forces, the variation of mechanical energy is equal to the work done by the resistive forces. Thank you for listening well this video, and don't hesitate to contact your teacher for any information. Wassalamu alaikum wa rahmatullahi wa barakatuh.